everyone. I'm Miss Curie from the Warrenville Public Library, and I am here with this month's Science Storytime to Go, and we are focusing all about space. So I'm going to go through a couple of the projects that I'm going to have you do, and then we're going to do a little bit of story time. I wanted to go through the challenge with you, so I'm calling it a space challenge, of course. And the three areas that we're going to talk about with our space challenge is making our own sundial. So first, we're going to learn about the astronomy and the chronometry, which is a fancy word for how to tell time. We are also going to do a little bit of gravity painting. So gravity talks about forces that play into our planets and where we live, and then also the viscosity, which is a fancy word for how goopy a liquid is, like paint. And then lastly, we are going to learn about some aerodynamics when we make our own paper rockets. So this is kind of an example of one of them that you are going to make. All right, so the first thing I'm going to do then is we're going to read our story. And our first story is called Space Heroes. So I kind of wanted to read a little bit about some of the strong women that work in space, both historically and nowadays. It's also Women's History Month, so perfect time to combine the two. All right, this is Space Heroes. Hopefully you recognize some of these names too. Out of this world. People who work at NASA are interested in space. They study space to learn more about it, and they also find ways to explore space. The women of NASA. Let's meet 4 women who did great things at NASA. Margaret Hamilton is a computer scientist. Nancy Grace Roman is an astronomer. Mae Jemison is an astronaut, and Sally Ride was an astronaut too. Nancy Grace Roman studies stars and planets. She is called an astronomer. Nancy helped to create the Hubble Space Telescope. Hubble orbits Earth. It sends back pictures of faraway stars and planets. Margaret Hamilton is a computer scientist. Margaret wrote a computer code for a spacecraft. The code told the spacecraft how to get to the moon. Sally Ride was the first American woman to visit space. Sally also liked teaching children about science, hoping that maybe one day, like you all, will become a scientist too. Mae Jemison trained as a doctor. She became a NASA astronaut too, and she was the first African-American woman in space. Endeavour is a space shuttle. It can carry 7 NASA astronauts into space. And these are the different parts of the rocket, right? So we have the cockpit, which is normally where your astronauts would be driving. Cargo bay, the nose, a wing, the thrusters, and the tail fin. Space shuttles need powerful boosters to get to space. First, the shuttle takes off. Then the boosters detach. Finally, the fuel tank detaches, and the shuttle is now ready for space. These women of NASA have helped us get to the moon. They have also helped us to learn more about space. They have changed our world, and one day you can too. The end. I love reading these Lego stories. I just think they're so cool. And then it teaches us just a little bit about some of the fabulous space heroes. You can always come into the library and check out more books if any of them really fascinated you. I didn't know about Margaret Hamilton and how her codes helped rockets get into space. So I think that's where I'm going to check out next. So in between our stories, I want to talk about one of our projects. And I thought I would touch briefly on our sundial. So this might look like a real silly like contraption, right? So the first thing you're gonna do is take your paper plate, and now I know my center, my rod is not in the middle, but that's okay. My timing will be off. My chronometry will not be exact, but that's okay. So what you wanna do is you wanna write the numbers on your clock, just like you would on a regular clock. Then you're gonna poke a hole through your plate, and that is where you're gonna put your straw through. Now, what I did was I cut 4 little slits on the bottom and taped them down so that way I didn't have to worry about my straw kind of getting all loosey-goosey. So I don't know if you can see, but what happens is when the sun shines overhead, so you're gonna have to put this out on a really sunny day, it casts a shadow. So I'm gonna use my phone flashlight so you can kind of see hopefully a little better. So then as, right, the earth rotates, it changes the time. Pretty cool, huh? Or changes the shadow, I should say, which then changes the time. It is all connected. So as you're making this and you set this outside, you're gonna wanna put it outside as close to noon as you can. So as you can see today, it is not noon right now. It's earlier in the morning. And then what you're gonna wanna do is go back at every hour and check to see if your shadows align. And some of the questions you can ask yourself is, why is the shadow moving? I kind of just mentioned it briefly. Is the sun moving or is the earth moving? Toward which direction does the shadow point? So you want to know, like, why is the shadow, if the shadow is pointing this way, does that mean it's 3 o'clock? Does that mean it's 4 o'clock? 7? What does it mean? Let me know what you think about all of those and if you have any more questions about your sundial. But I'm excited to see you make one and see if you are able to tell the time with it, which means that if you go outside at 3 o'clock, your sundial shadow should be pointing pretty close to the 3. And if it's not, we have to think about why. All right, now we're going to move on to our next story. This is called Your Place in the Universe. Now, the universe is a massive place. We are just a small little planet in a big old universe. And I think this story does a really nice job of kind of teaching us about our place and why our place is still important. So these kids are 8 years old. They are about 5 times as tall as this book. I always think that's funny. But only half, right? So if we piled 5 of this exact book on top of each other, that would be how tall those kids are. But only half as tall as this ostrich. Ostriches are the tallest birds in the world and may grow to be 9 feet tall. That's taller than 2 8-year-olds standing on each other's shoulders, but it's less than half as tall as this giraffe. Giraffes are the tallest animals on land. The tallest giraffe on record was 19 feet tall, which is more than twice as tall as the tallest ostrich. But giraffes aren't the tallest living things in the world. The tallest living things are trees. The tallest trees on Earth are California redwoods, and the tallest redwood is 380 feet tall. It's 20 times taller than the tallest giraffe, and it's still growing. But even it is not as tall as the tallest structures that humans have ever built. The tallest building in the world is more than 7 times taller than the tallest redwood, and people keep constructing taller buildings. But even these soaring skyscrapers are tiny compared to the highest peak on Earth. Measured from sea level, Mount Everest is 29,035 feet high. That's about 5.5 miles, almost 9 times the height of the tallest planned building, but even Mount Everest doesn't reach all the way to space. Although there's no exact height for the edge of space, it's commonly said to be 62 miles up. The International Space Station orbits 248 miles above sea. That's 45 times as high as Mount Everest, but it doesn't seem so far compared to the entire planet. Earth is 7,926 miles wide. That's 128 times the distance from sea level to the edge of space. From far away, the visible atmosphere looks like a thin blue film surrounding our planet. And the International Space Station doesn't appear very far away at all. Earth is enormous, but it's not so big compared to the orbit of the moon. Look at that. Earth, moon. The moon is 238,855 miles away from the Earth. It's so far away that 29 Earths could fit between the two. It's so far that a jet plane going 500 miles per hour would still take 19 days to get there. But even the moon is close compared to the sun. The sun, which helps with our sundial to tell us time, Earth is 93 million miles away from the sun. That's so far that a jet plane going 500 miles per hour would take more than 20 years to get there. It's so far that sunlight takes 8 minutes to reach Earth, and light travels 186,000 miles per second. But Earth is one of the closest planets to the sun. Could you imagine if we took one of our paper rockets that we're going to make today, and if we could ride that, and we rode it all the way to the sun, you would be 20 years older by the time you got to the sun. That's just wild. And there are still more planets. There are 5 planets beyond the Earth. The farthest is Neptune, which is 30 times farther from the sun than Earth is. The dwarf planet Pluto is 40 times as far, which is so far that sunlight takes more than 5.5 hours to reach it. Pluto is part of the Kuiper Belt, which has billions of comets and 4 dwarf planets. But that isn't the end of the solar system. Scientists believe that there are trillions of comets beyond the Kuiper Belt. The farthest of these could be 100,000 times farther from the sun than Earth is. It takes sunlight more than a year to travel that far, which would make the edge of our solar system more than a light year away. But our solar system is a tiny speck compared to the size of our galaxy. The Milky Way galaxy is 100,000 light years across and contains more than 100 billion stars. One of them is our sun. So it would take you, let's see, 27,000 light years, 27,000, oh my goodness, 27,000 light years from the center of the galaxy, which means that even if you could travel at the speed of light, it would take you 27,000 years to get there. But that's nothing compared to the distance to the Andromeda galaxy. Andromeda is the closest large galaxy to us, but it's 2.5 million light years away. It would take you 2.5 million years traveling at the speed of light to reach Andromeda. Andromeda and the Milky Way are part of a galaxy group called the Local Group. It has roughly 50 galaxies in it and is spread across millions of light years of space. But galaxy groups are small compared to galaxy clusters. Galaxy clusters are much larger than the galaxy groups. The Virgo cluster is the largest galaxy cluster near us. It has around 2,000 galaxies and is roughly 50 million light years away. But it's not the only one. Many galaxy clusters and groups surround Virgo, and altogether they are known as the local supercluster. But even our supercluster is just a tiny part of the cosmic web. Whoa. Huge chains of galaxies, millions of light years long, are strung throughout space. Clusters of galaxies are found where the chains meet, and between the galaxies lie vast empty regions called voids. This pattern is called the cosmic web, and it extends for billions of light years in all directions, like a giant three-dimensional net. And these are the largest structures in the universe. Whoa. Sorry for the glare, my friends. The universe is everything. Every star and every galaxy, every planet in all of space. It's the grandest environment we know of. And it may go on and on forever, but we really don't know. We don't know because the farthest we can see is around 13 billion light years away. Everything within this distance is called the observable universe. It's the region of space that we can see from where we are. So we can see 13 billion light years away from us, from right here on the Earth. In the vast cosmic web, in the Milky Way, in the solar system, there is a small blue planet called Earth. Earth is the only planet that we know of with life. It's the only planet we know of with trees, giraffes, and ostriches. It's the only planet we know of with kids who can look up and imagine. Who can imagine their place in the universe. The end. I know that was kind of a deep story, but it's really cool to think about how tiny we are, but how important we are in this billions and billions of light years galaxy, right? Okay. Now that we learned a little bit about where we are in space, let's talk about how we can get there by using rockets. So we are gonna learn a little bit about aerodynamics and physics. So all the directions are on your instruction sheet, but I kind of wanted to show you how I made mine in case you might have any questions. So the first thing you're gonna need is a straw. Now I've included some straws in your kit, but if you wanna use any other straws you have at home, that's totally fine. What I did with my paper is I folded it in half and then folded it in half again and cut it so that I had 4 rectangles. So this is half of a sheet, and I would cut this in half again to make the rectangle for your paper rocket. Then what you're gonna do is take the rocket or the paper for your rocket, and you're just gonna wrap it around the straw. So I'm sorry you can't see this part, but I'm rolling it up. So then it kind of looks like this, right? But you don't want to attach it to the straw. The straw is what's going to be your thruster to help get it into space. Then you're going to tape this down so that it stops rolling, and you will end up with a tube like this. You'll want to fold down and tape down the top so that it allows the air to stay trapped, which will help propel it forward, okay? And then you'll put it back on your straw, right? You want to leave a little bit of air though. You don't want to stick it too far in there, just a little bit. And then you're going to shoot it. Ready? Ooh, goes pretty far. What you can do then is you can measure it and write down how far it flew and then try again. See if maybe if you launch it higher up, if you take a deep breath, and propel it as far as you can with your breath. You can also do the optional part of making some fins. So what you want to do to make your fin then is take one of your rectangles and you're going to make triangles. So what I did was I took a corner and I folded it down so that it made an even edge along here. Then what you're going to want to do is cut off this extra little rectangle-y bit, okay? From that point, you should have a triangle that has a 90-degree corner. Okay, see that? You're going to fold it in half again. And then that's the part that you are going to tape onto your rocket to give it a fin. You're going to put it back on your straw thruster, right? That's important. That's how you get your energy to blast off. And then you're going to launch it again and see if there's any difference. Mine's not really going anywhere though. So I have to think about my aerodynamics for this then, right? What am I doing wrong with my rocket? Why isn't it launching? Is the air able to escape? So then my thruster isn't working? Has it gotten to be too heavy? And that's why? So these are all questions that you can think about as you're experimenting. And if this guy just doesn't work, use another piece of paper and try again. As you all know with science, failures are just as important as successes. Failures teach us what went wrong and how we can improve. So have fun practicing your astronomy, your aerodynamics, your forces of gravity, your viscosity, your physics in our space challenge this month. Until next time, I will see you all later. Have a wonderful day.